Hello, folks. Welcome to Science Talk. I'm your host, Jim Massa. Okay. Interannual variability of surface salinity and Ekman pumping in the Canada Basin during summertime of 2003 to 2017. This was published late October of 2021, and the authors are Zhihai Dong et al. Let's look at the abstract here. The Canada Basin, CB, is undergoing significant changes due to long-term global climate change and other shorter timescale processes that are still not well understood. Based on the in situ and satellite observations and atmospheric reanalysis data, interannual variabilities of sea surface salinity and Ekman pumping in the CB are investigated in the summertime of 03 to 2017. This study reveals strong surface salinity reduction and Ekman downwelling enhancement during 06 to 12 compared with the remaining years. The surface 20-meter salinity averaged in 2006 to 2012 decreases by 1.26 PSU, that's practical salinity units, relative to the other years. The results suggest that the lower surface salinity is correlated to enhanced sea ice melt and Ekman convergence in the CB. Enhanced downward solar radiation accounts for the accelerated sea ice melt over the southeast CB, leading to the surface salinity decrease. Right? Makes perfect sense. More sunlight, more melting, you're going to dilute the surface water. So that's perfect sense. Strengthened anticyclonic, clockwise, wind circulation over the CB not only enhances sea ice melt via strengthening offshore Ekman transport over the Chukchi sea slope, but also favors freshwater accumulation in the CB through strengthening the horizontal convergence. Sea ice melt is estimated to account for 54% of the surface freshening, and the horizontal convergence is believed to play an important role in the remaining 46%. During the freshening years in the CB, the Ekman downwelling enhancement is mainly attributed to variations of wind stress curl, sea ice concentration, and ice ocean stress curl. And the relative contributions are estimated on the basis of a linearized model as 72, 12, and 10% respectively. Okay, let's look at the plain language summary and then we'll discuss. The Canada Basin is undergoing significant changes due to complicated interaction between air, sea ice, and ocean. Atmosphere high pressure system over the CB accumulates the surface fresh water into the CB center due to the Coriolis effect. The accumulation leads to a relatively low salinity and downward currents in the CB. The observations during the summertime of 03 to 17 reveal interannual variabilities of the surface salinity and downwelling in the Canada Basin, CB. The surface salinity is remarkably decreased and the downwelling is strengthened in 06 to 12 compared with the other years. The analysis based on oceanic atmospheric data here demonstrates that these variabilities are mainly attributed to variations of wind circulation and sea ice. Okay. I want to point out this year right there, 2012. 2012 was when sea ice extent was the absolute minimum that has been recorded, which means, and this is summertime, that means there was a lot of fresh water on the surface. That fresh water on the surface is going to decrease the salinity. Now, they talked about enhanced, I already mentioned enhanced downward solar radiation, so that will increase the melting and so on. But there's a statement here in the plain language summary. The analysis based on oceanic atmosphere data attributed variations of wind circulation Okay. They are referring to, and they don't say it here, they are referring to the Arctic dipole. Where's the high pressure system? Typically, the high pressure system is located over the Canada archipelago. The low pressure system tends to be on the Eurasian side. If you have a high pressure system is anti-cyclonic flow. That means clockwise. Well, in the northern hemisphere, if you have anticyclonic flow, clockwise flow, that will, due to Coriolis, you have a deflection to the right, that will lead to a convergence in the center of basically a gyra. Because you got the wind blowing around, but the wind is going to impart wind stress. Now, the curl refers to when you multiply two vectors, when you do a cross multiplication of two vectors, the resulting vector is perpendicular to the two vectors that were just crossed. And if you have vectors, a situation where the curl is not conserved, i.e., it will rotate, then you're going to get this resultant vector that is perpendicular to the two that was just crossed. Some of you may be familiar with the so-called right-hand rule, right? You got your thumb straight up, you got your index finger pointing straight out, and you got your middle finger pointing straight out, and they kind of form like three axes, basically sort of perpendicular to each other. So if you took your thumb and crossed it with your index finger, the resultant vector will be your middle finger, and so on. It's called the right-hand rule. Well, if I've got surface flow that's rotating in a horizontal manner, think of that as crossing my vectors, and what's the resulting vector from that? It's going to be perpendicular, but if it's at the surface, perpendicular means it's in the vertical direction. And in this case here, with a convergence zone, the vertical direction is down. The Ekman downwelling enhancement, that's what they're getting at. That this is allowing for, because you're piling up the water in the middle, it has to go somewhere. You got to conserve volume. It goes down. That's basically what they're saying. So, but it is interesting to note that in this 6-year period, that was different from the other years that they were examining. And this goes to show you how there is some variability, and it would not surprise me that the positioning of the high pressure system, the low pressure system, comprising the Arctic dipole, was a major hand in this. And look at here, variations of wind stress curl, sea ice concentration, ice ocean stress curl. 72% attributed to wind stress curl. That is the pressure systems of the Arctic dipole. It's right there. They quantified it. It's right there. So this goes to show you how, again, we can have how things are rapidly changing. Now, I just did my last video I just did. We talked about how the surface salinity is actually increasing. Well, keep in mind what they're talking about here is this, that period of 6 years where the surface salinity is decreased because of all that ice melting at the time. As we lose the ice in the first place, as is what is happening, and what I was trying to address in that previous video, as you lose the ice, well, then you're not going to have ice to melt to dilute those surface waters, i.e., decrease the salinity. So basically, a lot has happened in the last decade. So it goes to show you how dynamic the system is. And, we're trying to piece together all these bits of information, but overall, we're understanding better the oceanography, the physics of what's happening up there, and it's helping us better understand what it means, not just for the Arctic, but for the planet. And by the way, okay, surface 20 meter salinity in this time period decreased by 1.26 practical salinity units. May not sound like a lot. That's a big difference. That is if you're decreasing, that will temporarily, at least in the summertime, lead to stronger stratification, at least in the surface waters. Recall that my previous video, they were just looking at the wintertime. But 1.26 PSU difference is big. That's huge. Another study showing how things are changing in the Arctic and what a dynamic place it is. We'll talk soon. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.